Good morning. Before we carry on with the chapter on DC speed control, let's just have a look at the shunt motor and the series motor. There we have the equivalent circuit for a shunt motor. And the formulas that we are going to use is E1 is equal to V minus IARA. And the field current is the voltage divided by the field resistance. Then we can say that E1 over E2 is flux 1 divided by flux 2 N2. And we know that flux is directly proportional to field current. Therefore, we can say that E1 divided by E2 is I field 1 N1 divided by I field 2 N2. This is known as the speed change formula. T1 over T2 is equal to IA1 flux 1 divided by IA2 flux 2. This is equal to IA1 I field 1 and IA2 I field 2. This is known as the torque change formula. Now, to be able to change the speed, we can either put a resistance in parallel with the field, in series with the field, to reduce the current in the field. And therefore, the machine will start running faster to attain equilibrium, because it always needs to be there. So if we change the speed lower than base speed, we can put a resistance in series with the armature. Then let's look at the series motor. There's your equivalent circuit, where we have E is equal to V minus IA times the sum of RS and RA. E1 divided by E2 is I1 N1 over IA2 N2, also speed change formula. And T1 over T2 is IA1 squared divided by IA2 squared, which is again the torque change formula. Now, to be able to do the speed control, we can either put a resistor in parallel with the field, or we put the fields in parallel, or we can change the voltage. Now let's look at an example. A 250 volt DC shunt motor has a shunt field resistance of 250 ohm and an armature resistance of 0.25 ohm. For a certain low torque, the motor speed was 1,500 revs per minute, taking an armature current of 20 amp. If a resistor of 250 ohm is connected in series with the field, the low torque remaining the same, we must compute the new speed and armature current. The magnetizing curve is linear. Now, since the magnetizing curve is linear, it means that the flux is directly proportional to the field current. So N2 over N1 is equal to E2 divided by E1 times I shunt 1 divided by I shunt 2. And we calculate IF2, which is V divided by RF, which is 1 amp. In the case where we've got the 250 in series, that means our current is now halved. Torque 1 is equal to torque 2. That means I field 1, IA1 is equal to IA2, IF2. And therefore, IA2 is 20 divided by 0.5, which gives us 40 amp. Now, E1 is V minus IARA. That is 250 minus 20 times 0.25, which gives us 245 volts. Now, in the second case, E2 is equal to 250 minus 40 times 0.25, which gives us 240 volts. Then N2 over the 1,500 is 245 times 1 divided by 240 times 0.5. That gives us that the speed is N2 is 2930 revs per minute. On to the next example. A 250 volt shunt motor has an armature resistance of 0.5 ohms and runs at 600 rev per minute on full load, taking an armature current of 20 amp. If a resistance of 1 ohm is placed in the armature circuit, compute the speed at full load torque at half full load torque. Now E1 is V minus IARA, 250 minus 20.5, that gives us 240 volts. Nothing is done to the field, so the flux 2 is equal to flux 1. Therefore, torque 2 is equal to torque 1, which means it's constant. Therefore, IA2 is also 20 amps. So, E2 is V minus IARA, 250 minus 20 times 1.5. That gives us 220 volts. N2 is therefore 550 revs per minute. Now, question 2, half full load torque. T2 is equal to half of T1. That means IA2 is 10 amps. E2 is then 250 minus 10 times 1.5 is 235. And again, N2 over 600 is E2 over E1. And therefore, N2 will be 587.5 revs per minute. On to the next example. A 250 volt shunt motor has a field resistance of 40 ohm and an armature resistance of 0.02 ohm. It takes a current of 55 amp and runs at 595 revs per minute with a resistor of 0.58 ohm in the armature circuit. The torque is constant, and what should the armature resistance be to raise the speed to 630 revs per minute? Now, I shunt, again, V over RF, which is 5 amp, and therefore the armature current is 50 amps. And if we now calculate E1, it's 200 minus the sum of those two, which gives us 0.6, is 170 volt. And since the torque is constant, IA1 flux 1 is IA2 flux 2. And since the flux are the same, the current will be the same. So therefore, N2 over N1 is E2 over E1. And we have E2 is 170 times 630 divided by 595, which gives us 180 volts. Now compute the speed of the motor if the load torque is reduced to 15 amp. So let R2 be the new value of the armature circuit resistance to change the speed from 595 to 630. So there we can see that 180 is equal to 200 minus 50 R2, and therefore R2 is 0.4 ohm, and therefore RA must be reduced to 0.4 ohms. That means we have to remove 0.2 ohms. Then thirdly, now suppose a 5 ohm diverter is connected across the armature and the series resistance is adjusted at the motor speed again is 595 revs per minute when the armature current is 50 amp. We must compute the speed when the motor runs at current when it falls to 15 ohm again, 15 amps. When the motor current falls to 50 amp again, sorry. So IA2 is 50, and therefore E1 is 170, and N1 is 595 revs per minute. IA2 is 15 amps, and E2 is 200 minus 15.6, which gives us 191 volts. N2 over N1 is E2 over E1, And that gives us a speed of 668 revs per minute. Now with an armature diverter, let R be the new series resistance. Therefore, E2 is 200 minus 50 times 2, which is 199 minus IR. Since the speed is 595, E3 must be 170 volts. So 170 is equal to 199 minus IR, and therefore we find that IR is 29 volts. Now the voltage drop across the diverter is 200 minus 29. That gives us 171 volt. And the diverter current then will be 171 divided by 5 ohm, which gives us 34.2 amps. So therefore, the line current will be 50 plus 34, which gives us 84.2. And IR is 29. So R is 29 divided by I, that gives us 0.344 ohms. With IA is 15 amps, I diverter is I minus 15. So 15 times I minus 15, 5 times I minus 15 is 200, minus 0.344 I, and therefore I is 51.46. So therefore, E4 is 200 minus 0.34 I minus 15 times 0.2. That gives us 182 volts. So N4 over N1 is E4 over E1, and that gives us a value of 637 revs per minute. Right, let's look at series motors. As I've said, we've got speed control, we've got the flux control method, and therefore we can say it's field dividers, armature divider, tapped field control, and paralleling of the field coils. There you can see for the field diverters, the speed is above base speed and the armature divider speed below. Tapped field is the field that's got tappings and it can be switched between taps. Or the field coils can be connected in parallel. And then we have a variable resistance in series with a motor. Okay, example. A two-pole series motor runs at 707 revs per minute when taking 100 amps at 85 volts with field coils in series. The resistance per field coil is 0.03 ohm and that of the armature is 0.04 ohm. If the field coils are connected in parallel and the load torque remains constant, we must compute the speed and the additional resistor in series with the speed at 707 revs per minute. Now, since we've got a two-pole, there's two coils, so Rm is 0.04 plus 2 times 0.03, that gives us 0.1 ohm. Therefore, E1 is 85 minus 100 times 0.1, which gives us 75 volts. Now, with the field series windings in parallel, the current through each one is half the armature current. So IAT is equal to the new armature current is divided by 2. Torque is constant, and therefore we get that flux 1, IA1 is flux 2, IA2. And that is 100 squared is IA2 squared divided by 2. That gives us 141.4 amps. So E2 is now 85 minus 141.4 times 0.04 plus 0.015. Remember, the two coils are now in parallel and the resistance is divided by 2. So N2 over 707 is 722 divided by 75 times 100 divided by 141.41 divided by 2. That gives us a speed of 1029 revs per minute. Now here on the right hand side, we see that flux 2 is IA2 over 2. And if we apply the formula E1 over E2 is flux 1 N1 divided by flux 2 N2, we get that N2 is equal to E2 flux 1 N1 over E1 flux 2. Right, let's look at example number 5. A DC series motor having a resistance of 1 ohm drives a fan which the torque varies with the square of the speed. At 200 volt, the set runs at 350 revs per minute and takes 25 amps. The speed is to be raised to 500 revs per minute by increasing the voltage. Compute the voltage and the corresponding current, assuming the field is unsaturated. Since this field is unsaturated, the flux is directly proportional to the armature current, and the torque is directly proportional to IA squared, and torque is directly proportional to N squared. So we get that IA squared is equal to N squared, and IA2 is then N2. So IA2 over IA1 is N2 over N1. That gives us that I2 is 35.714 amps. So E1 is 220 minus 25 times 1, which gives us 195 volts. E2 is V minus 35.714 times 1. Now flux 1 over flux 2 is 25 divided by 35.714, which gives us a value of 0.7. So flux 2 is equal to 0.7 flux 1. N2 over N1 is E2 flux 1 divided by E1 flux 2. It's 500 over 350 is V minus 35,714 times 0.7 divided by 195. That gives us a voltage of 438.7 volts. Okay, example 6. A 220 volt DC series motor takes 40 amp when running at 700 revs per minute. Compute the speed at which the motor will run and the current taken from the supply if the field is shunted by 0.1 ohm and the load torque is increased by 50%. RA is 0.15, RS is 0.1 ohm, and the flux is directly proportional to armature current. So the torque proportional to IA squared, and therefore T1 is IA1 squared is 40 squared. So IA2 is the new current, only half of that will pass through the field. So there we have IA2 is equal to IA squared 2 divided by 2. T1 over T2 is IA squared divided by 2 times 40 squared. And remember, T1 is increased to 50%, so 1.5 is IA squared over 3,200, which is 40 squared times 2. And that gives us a current of 69.3 amps. So E1 is then 220 minus 40 times 0.025, which gives us 210 volt. And E2 is now 220 minus 69.3 times 0.2, which is 206.14. Then we say N2 over N1 is E2 flux 1, divided by E1 flux 1, 2. So that means we've got N2 over 700 times 206.14 times 40 over 210, and then the second current divided by 2, and that gives us N2 is 794.0 revs per minute. Sorry, that must be flux 2. Okay, example. A 200 volt DC series motor runs at 500 revs per minute when taking a current of 25 amps. RA is 0.2 ohm, RS is 0.6 ohm. Compute the speed when the diverter of 10 ohm is connected across the armature. Assume the magnetic saturation, that no magnetic saturation occurs. So that is our equivalent circuit there. So we have E1 is 200 minus 25 times 0.8, which gives us 180 volt. I2 is the new current, so VRS across the shunt field is 0.6 I2, and VB is 200 minus 0.6 times 2. So that we have there, the volt drop there is equal to the volt drop there. So IA is 200 minus 0.6 I2 divided by 10. And therefore, that's the diverter current. And then we have IA2 is I2 minus 200 times 0.6 I2 divided by 10. That means IA2 equal to I2 minus 200 times 0.6 I2 divided by 10. And if we finish that equation, we find that IA2 is equal to 10.6 I2 minus 200 divided by 10. And then torque squared, 25 squared, which is the current, is I2 10.6 times I2 minus 200 divided by 10. And if we solve that equation, we find that IA2 or I2 is 35.6 amps. So VB is 200 minus 35.6 times 0.6, that gives us 178.6 volts. So if we substitute it back into that equation, we find that IA2 is 17.74. Therefore, E2 is 178.6 minus 17.74 times 0.2, which gives us 175 volts. And N2 over N1 is E2 flux 1 over E1 flux 2. And that gives us a speed of 340 revs per minute. I hope this helps in the exercises that you have to finish. Thank you.